What?
Let him
Man,
cook now.
We're morbing in.
Let him
We're
cook.
morbing in.
I said let him cook.
It's morbid time.
Hey, Charlie, let's do this question right here with Stacy Spring Break. Let's check it out. How you doing, Charlie? Let's jump into it. I was going to do the other chapter, but you are here. So it's your questions. Okay. I think I've got it. Jumping good. Chapter 14 is confusing too. Chapter 14 is a tough one. It takes a lot of practice to get these chapters down. And we should have this Stacy question here in a second. Okay. Trying to find it. Or that's close. It's on the quiz, not the homework, right? There it is. What are the three, let me mark this in the notes. What are the three conditions for the sampling distribution of the sample proportion? What are the three conditions? Don't worry about the question asked. Never worry about the questions. Worry about the knowledge. That's not the answer. What are the three conditions for the sampling distribution of the sample proportion? What are the three conditions for the sampling distribution of the sample proportion? Condition 1, random. Charlie's got it right there for 5,000 points. We got random, 10%, and success failure. We go back to the notes back over here. I was getting my lunch. I went on a nice little walk, and someone coughed on my lunch. They coughed on my lunch while I was eating it. And germaphobe Brian had to throw it away because I'm a germaphobe. There's the random 10% success failure. We went over that today in class. So I got some goldfish. I got some Vita water. So I'm on a nice little walk. Going to walk. So did she randomly collect students, yes or no? Did she randomly collect students, yes or no? Oh, yeah. Oh, yeah. Randomly collected students. Now, you got to pretend Stacy goes to UT. Why am I saying let's pretend Stacy goes to UT with 100 students? Because if Stacy goes to UT, she randomly collected students, which meets condition 1 that this is randomly collected data. And since she goes to UT, 100 students would be what? 100 students would be what? Since she goes to UT, which we were kind of doing it right here, and ironically, this is already set up for the problem. Since she goes to UT, 100 students would be what? We're pretending she goes to UT. Well, since she goes to UT, her sample of 100 is less than 10% of the population. This is the math you need to remember, is you take lowercase n, which is sample size, and divide by capital N, which is population size, to see if it's less than 10%. And you can double check the math right here, but it's going to be less than 10%. So we go here and do 100 divided by the size of UT. And that's not even, it's a fraction of a percent. It's 0.26%, or 0.0026 is a fraction. But if she believes 7% of the students will go to spring break, how many successes would she expect out of 100? If she believes 7% will go to Florida, how many expected successes are there? And for these problems, you'll see it when we look at the notes right here. You have to identify N, P, great job, Charlie, right there. And you have to identify Q. Charlie on fire right there. And there's Q. So now you have to do NP and NQ, and NP is going to be 100 times 0.07 equals 7, and 100 times 0.93 equals 93. There we go. And do we pass? Alexis? Yeah, let's do it. We'll do some of those, Alexis. Yeah, drop the questions in the chat. We'll talk over them real quick. Awesome. So do we pass the at least 10 successes, at least 10 failures? Yeah, let's do automatic card reader next. You got it. And so we do not pass at least 10 successes, at least 10 failures. So we don't pass success failure. So that's got it. An automatic card reader is trying to read things. Here we go. Automatic card reader trying to read things. You got it. Drop the questions you want done. I'll do as many as I can, as quickly as I can. And then answer the questions too. I love when people answer questions because then we do even more, even faster. An automatic reader. Let's do it. This one's you'd be shocked. When they send out fundraising, you got it. We'll do it next year, Charlie. After this one. Here we go. So this one is mainly looking at the success failure condition. Automatic. So this one is looking at the success failure condition right here. And when you look at it, you need to know the probability of success or the proportion of time success occurs. What from the problem is the proportion of time success occurs? What is the proportion of time? Read the problem right here. What is the proportion of time success occurs? The proportion of time success occurs is what? What is the proportion? 84. So what's the proportion of time failure occurs? What is the proportion of time failure occurs? If the proportion of successes is 0.84, what's the proportion of failures? Well, we got a lot of good questions in chat. Ooh, and we got people answering quickly. I like this. Ooh, we got some strong office hours today. So now we need to check for different sample sizes of 20, 50, and 75, and 100. Now, the one that's going to cause problems is going to be this, because remember, NQ needs to be greater than or equal to 10. Well, NP is the big one, so 84% of something's the bigger portion. So NQ is going to give us problems. So we can do NQ relative to a sample size of 20, 50, 75, and 100. So we're just multiplying it by Q right there, which is 0.16. That's NQ for all of them. Who follows me that N is what's changing and Q is still 0.16? It's saying if we give it 20 cards to read, what probability of failure is it? 16% probability of failure on 20 things it's reading. So we would expect about, doing the math in my head, times by 2, move the decimal, 3.2. Take half of it right here, and then take a quarter. So this would be 12, and this would be 16. So there's the answers, expected successes. So this is literally NQ. Where do we have a large enough samples? It's not really a large enough. That's not what the condition is called. When do we meet success failure? At 20, 50, 75, or 100? When do we meet success failure? That's what I was checking right here. I was checking success failure. So when do we have at least 10 successes, at least 10 failures? When did we get at least 10 successes, at least 10 failures? There's how to do it right there. That's the math. When did we get at least 75? Yep. So if you look right here, we met it right here. That means the distribution will be normal right there. So after that point, it's normal. It just gets more normal. So it's normal if there's at least 10 successes, at least 10 failures. So that goes to the shape of the distribution. It'll be unimodal, symmetric, normal. And the earlier ones are more left skew. This is when it normalizes. Don't look at the pictures because you'd be like, oh, 50 looks kind of normal. Still a little bit of left skew. So it still has a left skew to start until we get the large enough successes and failures. The next one, where the mean is at, is a little tricky. The mean is usually contained, like, if you remember the formula, that mu p hat equals p. So the center of the distribution should be around 0.84. And if you look, do you see how 0.84 would be within here between 0.8 to 0.9? 0.84 would be between, and I'm looking at this one, here's 70, 75, 80 to 85. So 0.84 is within this range. It should be. That's where the peak is at we're looking for. The next one is, this is 70, 75, 80, and that's 82.5 to 80. So at 0.84, whatever, it does contain 0.84 the peak. And it usually does, sometimes 0.84 is on the, like, on one of the boundaries, which is annoying. Then this one, 75 is in the middle, and that's 80. And this one looks to be 84 to 86 because that's 85 right there. So the peak is 82 to 84. So it's in the range on all of them. It's contained within the boundaries. The mean is the true proportion. And the last one is 82 to 84 because 75, 80, 85, and then this is going to be where 84 is at. Not 84. This one's not 84 to, and yours might be different. You have to look where yours is at because this is the 84 to 86. So it looks like it's, and we could label everything very carefully right here. Like I'll show you. If you want to be really exact, you'd go in here and you'd go 76, 78, 80, 82, and then this is 84. And if you notice, that's where the peak is at right there. So the peak is at 82 to 84. Does that make sense, Coda? If you label more numbers on the axis, you have to be very careful on how you look at it. But I hope that kind of makes sense where the peaks are at. So the center of the nice job, Coda. The center of the distributions, 84. Whoops, we'll do that last one here. 84 is contained within, like 84. It's usually, problem is when it's on the edge of things, it's harder. And then 84 is on that one, and then this one's on the 82 to 84, somewhere the top is. The last one's the spread, which is literally, what is the spread of this one? This is the big one, the last one, the big sample size. So what's the spread? You can do negative if you want, but so what's the spread of this one? What is the spread of it? We got a lot. 0.2. Nice job, John, right there. Yep, 0.2. And this one's 0.5. Just the difference between those numbers, 0.35, 0.35, and 0.2. So the spread was greater than this. This is the wide run, the 0.5, the very first one. And then the next one's 0.35, so that's between these numbers. The next one was 0.35 also, because we're looking at this. This is 0.35. And then the last one's 0.2, which is more narrow of a range. Wait, 0.2. There it is. That should do it. And here we go. More questions. Let's do it. Next one is, we did automatic character reader. Fundraiser. We'll try to switch over to the other thing here in a moment. Oh, that's another automatic card reader? It's the other version. It's very similar. I think this is it, the fundraiser dinner. This will be quick. A quick question. Okay. So if you look at it, they're talking about what happens to the distribution. When you increase sample size, what happens to the mean of a distribution? When you, Gallup, you got it? So when you increase sample size, what happens to the mean of a distribution? If you increase the sample size, what happens to the mean? The answer is on the slide. If sample size increases, mathematically, the mean does what? Should stay the same. It basically does. Theoretically does, but in like simulations or practice, it might move slightly. But theoretically speaking, the mean will stay the same because here's two slides with both the mean on it. Mu p hat equals p. So whatever the truth is, regardless of the sample size, the expected, and we have this down below, the expected sample mean or the expected sample proportion is equal to the true value of whatever that is. This would read expected sample proportion is equal to the true proportion. I think, yeah, we'll do that. I think we'll do that one because I just did the other version. So the center of the histogram, which is where the mean is at, if you notice, is right about here, 0.83 or so. Wait, is that? No, that's not 0.83. That's like 0.9. 0.9. Notice it's still here at the same spot. They moved the axis. I wish they didn't do that. But it's somewhere around 0.925, 0.925, 0.925. And because of the scale difference, it's still around 0.925. But what is getting smaller? Very important thing to know. That the mean stays the same, but what decreases? Notice the distribution is doing this. So what is decreasing as sample size increases? And the answer is on the current slide. What decreases as the sample size increases? You can see it mathematically here as I mess up the equation. What decreases? So as sample size increases, what decreases? As sample size increases, what metric decreases? Very important note to have about the central limit theorem. The standard deviation, exactly. Because just think mathematically, if n gets bigger, like as n increases, you're dividing by a bigger number, which makes this quantity smaller. So the standard deviation, and you see that because there's less spread to the data. Do you notice how this data goes from 0.75 to 1, but at the end, it doesn't even go to 0.75? So we would say the center stays about the same because the mean doesn't change. The shape becomes more normal as sample size increases. So shape becomes more normal. And the variability, which is standard deviation, is going to decrease, and these simulations do appear to show this, and that's got it. Okay, I think the other automatic card reader one, I think this is the one they wanted. Correct me if I'm wrong. We'll do another question right after this. We're just reviewing, getting these questions down. Okay. Great job, Mia. Okay, here we are. So this is the other automatic card reader. Now, what do you want to do with questions when you get them? This question's already done it. Gallup, we'll do that one next. You got it, Charlie. So what do you do with a question, which this one's already done? When you get a question, you should do what? And this question's already done a lot of this work for us right here. And we can figure out one more thing from that. What do you usually do with a question first thing? Leo knows. Leo always knows.
Notation, brother.
Leo was a student in the class. Label that notation. Notation, brother. He would say that when Leo was in class. He might have graduated. I saw him last semester or so. But he would say, notation, brother. So I made a meme out of it, and he loved it. So, or he liked it. I don't know. Maybe he hated it. So P and Q are complements of each other. P is the proportion of successes. Q is the proportion of failures. And then we have relative sample sizes that this is done for. But here's the thing. If we want to know the shape of these histograms, the shape will be normal if we pass how many conditions? The shape of the histogram of the distribution of the sample proportion will be normal if we pass how many conditions? The shape of the distribution of the sample proportion will be normal if we pass how many conditions? 3 conditions. I can't find them. They're on here somewhere. Here they are. Random, 10%, and success failure for the distribution of the sample proportion. So if we have NQ is the small one, then with a sample size of 20, 50, 75, or 100, we simply multiply by Q, which Q is going to be 0.15. If we have a sample size of 100, how many expected successes would we have? So I'm asking this lowest one. How many expected successes would we have with a sample size of 100? You just multiply these. Just multiply equals this. Or failures. This is failures technically, but you can flip-flop. How many expected failures do we have with a sample size of 100? 15. And you can go work through all the mathematics right here. I think this is it going to be 4 points? No, it's not going to be 4.75. It's going to be, it can't be 4. I'll just cheat. 15 times 75 divided by 100. That's not how you do math. Here's how you do the math. 75 times 0.15. There it is, 11.25. Ooh. And that's multiplying 50 times that, and this is this. Why am I happy with this number right here? Why am I happy with that number? Why am I happy with 11.25 when doing the success-failure condition? It's greater than 10. As long as you have at least 10 successes, at least 10 failures, then we will have a normal shape. So 75 would be the lowest amount because that's when we have at least 10 successes, at least 10 failures. And that's what it says. We have at least 10 successes, the value of NP are both at least. There we go. That should do it. There we go. We got Charlie's question coming up here next. Charlie said, and then we'll probably jump to Alexis's one. When they said, can you do fundraiser philanthropic, right, Charlie? Haven't done that one yet. We've done a lot of these. Fundraiser philanthropic. That one's an easy one. What was it? Suppose 30% of people, what is the standard deviation? Well, it has to be the decimal one. The other ones are not the answer. Suppose, what proportion do you expect to see? That's the proportion. There we go. As the sample size increases, the standard deviation of the sample distribution gets smaller. The mean stays the same. Oh my gosh. Well, I can destroy this one really quick right here. That's not normal, so you can't use it because it's skewed to the left. It's not normal, so it's based on the normal curve. There you go. Okay, so we only have these ones left. Gallup. Actually, Charlie wanted Gallup, so there we go. Gallup question. Here we go. Let me mark it in the notes. We'll have done all but 2 questions on this quiz. Automatic character We did that one we actually just did one version of that, and we did it 8 minutes into the stream, Maddie. We could swing back to it. It's in the notes, so if you want later, it's right here. It's saved already. It's at the 8-minute mark, and we just did a different version of it a moment ago. Thank you, Maddie, for being here. 5,000 points. We might try to circle back to it. But we're going to knock out as many questions as we can. Okay. 23, 4 to 3. Taking the note for the question. Boop, boop, boop. Okay. And Gallup early. Okay. Gallup is going to talk to people about something. And with this, they collect data and they find out that 48.81% of people in their sample of 20,006 are thriving. So what does the p hat mean? Now, here's the thing. What is p hat as two words? Something, something. Don't even worry about this question. You have to know what p hat is. What is p hat? What is p hat? What is p hat? Just what is it? P hat is always relative to n. You always have to have an n. But two words to summarize what p hat is. What is p hat? Anyone know what p hat is? Sample proportion. So you have to have a sample size because that's how many people you talk to. And this is the proportion of that sample that answered the question in the affirmative. Whatever you're asking, like, are you thriving? Yes. Then yes, the proportion. And it might, and then we'll do that one here next, Mia. You got it. And then that might wrap it up. Oh, you just finished the course. So this is the sample proportion. So p hat is the researcher's sample proportion. 48.1% of the sample were classified as thriving. This is the researcher's best. Was it B or C? Is p hat our best estimate of p? So do we use the sample proportion to estimate the sample proportion? Or do we use the sample proportion to estimate the true proportion? I'll answer my own question. The answer is C. And then calculate the standard error. So we wrote some equations today in class. I guess a little bit higher up. The standard error is an estimate of the truth. Am I hallucinating? Hopefully not. The standard error is an estimate of the truth. Here it is. Where the standard deviations are the truth. So you've noticed the difference when it's the standard error, you use p hat, q hat, which are estimates, versus standard deviation of the sample proportion uses the actual truth. Standard deviation of y bar is sigma over square root of n. The standard error of y bar is s over square root of n, which is the sample standard deviation. There we go. So all we do for this question is note what is p hat, what is q hat, and what is n. Remember, the equation is p hat times q hat over n square root. I'll write it so you can see it. The equation for the standard error of p hat is equal to p hat times q hat over n square root. And so we simply just plug in the numbers right here of 0.4881 times, and then q hat, 1 minus p hat, and then that's going to be 1 minus 0.4881. And that's going to be 0.5219. And divide this by 20,006 square root. And we solve out. There it is. Copy the number from your calculator on your computer, paste in the number, and then be very careful. It wants to 7, you gotta be kidding me. 1, 2, 3, 4, 5, 6, 7, and then round. And the standard error is based on estimates. The standard error is the best estimate of the standard deviation, and it's relative to a sample size. There we go. That should do it. Really? It's not this, is it? It is this. Uh-oh. Where'd I make a math error? 1, 2, 3, 4, 5, 6, 7. So I must have made a math error. But let me do... There's p hat. There's q hat. P hat times q hat over n square root. Ooh, there was a math error on that. Man, such a tiny error. something like that for the decimals. There you go. Math error. Math error. Maybe we'll just do the last. I got the last two. Okay. This question is virtually identical. So wait, Maddie, I want you to help me out right here. We're going to do this one, but it's virtually identical. Very similar concepts. You ready? So with this question being virtually identical, help me out. What is p hat again? P hat is the what? Don't even worry what the question is. Just what is p hat? It says they went out and talked to kids and 44.6% were online almost all the time. So what's p hat? Just like what is p hat as 2 words? We said it earlier a second ago. What is p hat? Just what is it? Well, expected is mu p hat. That's if we talk about the expected sample proportion, which we do in this chapter. That's the idea of mu p hat. That's expected sample proportion when we do a sampling distribution. P hat itself is just the sample proportion. P hat is found by doing x over n, which is just the amount. Like if you talk to 10 friends and 2 of them have cats, then you would have a sample proportion from your sample of 10 friends, 2 owns cats. And so p hat is the sample proportion. Oh, Mubot's here. What's up, Rotowave? I saw the Mubot.
Rotowave, you are the best. Please keep coming to the stream. We hope you're doing well. Mubot is going to give you more points.
There we go. So the sample proportion is what percent of the time something occurs in a sample. So p hat. So which of these answers look right to you? A, B, C, or D? A, B, C, or D? Which of these look right? The percent of proportion that occurs in a sample. There's a little bit after. You narrow it down to 2. Which of these look right? Which of these look right? Mubot will be nice to us all. He'll save us all. Nice job, B or D. You're right, Maddie. And then with that, p hat is an estimate of p, the true proportion. Like you're trying to figure out the truth for everybody, which is p. P stands for the true proportion. Like 40% of students are in state. That's p. I talked to 100 students and 40 of them were in state. That's still 0.40, but that would be out of 140 were in state. So that would be p hat. So if it's like, we know all students are in state, p. Rotowave's got all the points. We know 40% of students are in state, p. Out of a sample 100, 40 were in state, 40 is x, and then 40 divided by 100 is p hat. It's still the same numbers, but the phraseology is different of it. Phraseology, sure. This problem also is similar to the last one, where the equation is p hat times q hat over n square root. So we have to take this question and run it through the same formula. And so here it is. Well, the sample size is up there. Where's the sample size? Sample size is here. Cool. So to get the standard error, which is an estimate of the standard deviation, we need to know P is 0.446. Q is 1 minus P. Or we're doing P hat right here because we're doing standard error. And that equals Q hat. So Q hat is equal to 0.554 because these have to add up to 1 if you're checking your math because 1 minus P hat is Q hat, their complements. And then the sample size is this. So sample size is 1058. I cannot write. And so now we just run it through the math of P hat times Q hat over n square root is equal to the standard error of y bar. And we put through the formula. How is this looking good, Maddie? There we go. You're welcome. Great work. Thank you for being here. We'll do the last one. We'll have done every single problem. Literally all of them. Went fast today. It's like I drank a Red Bull, but I didn't. I didn't drink a Red Bull. Tell them. 1, 2, 3, 4, 5. Okay. Very careful on the decimals on this. Make sure to round. The standard error is the best estimate of the standard deviation based on a sample size of that amount. And there it is. Standard error is an estimate of the standard deviation. I have a slide showing that we made today, that standard errors are based on samples. And you can see it right here, where the standard error is based on a sample, and the standard deviations of like y bar are based on truth, where the standard deviation of p hat is based on the truth. There we go. And the last one. Okay, here we go. Last question. We've done every single quiz question. Kind of did some secretly though. I like this one a lot. This one's really good. Okay. It says the proportion of adult women is 51%. So what did it just tell us? Remember, we do notation. So anyone in the chat want to help with this one? Then we're gonna do some chapter 14. We might just do the full homework. That'll get people set for success. So what did it just tell us when it says the proportion of adult women is 51%? It says approximately. It just should say is. What is it saying approximately? What does that tell us? The proportion of adult women is 51%. So what do we know now? What notation can we write? It says a marketing survey went out to 340 people. That's N. So the proportion of adult women is what? Well, I mean, but what is it notation-wise? What do I want to write right here? I want to write like equals some value. What do I want to write? Whoop. Give it a moment more. P. Nice job, Mia. Yep. P equals 0.51. As soon as you find P, you find Q. Q equals 0.49. And then it says, what is the expected proportion? Well, expected proportion is mu P hat. That's expected sample proportion. Because it says out of a sample, like out of this sample, yeah, expected sample proportion. So that's equal to P. So do you know what the first answer is? The next one says right here says, what is the standard deviation? P hat. That's just going to be P times Q over N square root. So we just plug in the numbers right here. We plug in 0.51 times 0.49 over and 340. And the last one is how many, so we just solve that. Do you know what the first answer is? It says, what is the expected sample proportion? So the first one is this equation right here. This one, standard deviation. This says, how many women would you expect? We'd expect 51% of the 340. That's how many we would expect. And the first, does anyone know the first answer? What goes in this box right here? Seeing if people get what's written right here. What's the answer to that one right there? I mean, I basically have it solved out because I wrote mu p hat equals P. That's the answer theoretically. That, yeah, I mean, you didn't. I like it. Yep, 51%. Because if 51% of women are, if 51% of people are women, I expect 51% of my sample to be women. And then we do P times Q over N square root. There we go. And then we take 51%, which I should be able to do 51% in my head. Boop, 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 boop. I got it. Yeah. And it was 0.4. 51% of 340. There we go. Rounded down. There we go. I did not make robot sounds while doing that. There we go. That's the math is on the screen right here for it. There it is. You just take it's expected successes because it's N times P. So that's how many expected successes do you expect to have? There we go. Well, should we do you want to do the full homework, Mia? We'll do the full homework. How is this one open still? I don't know. I don't even know. Did anyone take any? No one took any other notes today. Only my notes, cheat sheets. Yeah, let's try to do the full homework. I'll do a bit right here. I don't know. My stomach's been aching today. It's like, ugh. I'm on my amoxicillin because of my root canal. Next Wednesday, I'll have to cancel office hours next Wednesday. Oh, it's good. It's right after the test. Yes. Because I have to go do a screening appointment. I'm sorry, Alexis. I have to do a screening appointment for my tooth. So I have to go do that next Wednesday, which I guess is perfect. I say, but I teach. It's so funny when I was at the dentist office. I don't. So I went to the dentist office and she was making an appointment for me and she's like, okay, how about noon on, she goes, okay, so we have you set up for noon on Thursday or something. And I was like, I can't do that. And she was like, oh, you can't. I was like, I teach. Okay. Here we are with the homework. Let's try to do as much as we can. They're like, what? You have a job? You? He didn't say that. Okay. Chapter 14, homework. Okay. This is a food company weighing salmon. So when they weigh the salmon, the number one thing to know about this is notation, brother.
Notation, brother.
You got to know your notation. If you don't know notation, these problems are way harder. It says the boxes have an actual weight of 34 pounds. That makes this mu. The boxes have a standard deviation of 3. That makes that sigma. It's like a true statement. Like, oh, we know that our boxes have a weight of 34 on average. And we know they have a variation of the weight, which is standard deviation of 3. Then we're asking for different sample sizes. A sample size of 4, sample size of 36, and sample size of 64. Now, what's really nice about these numbers is they're perfect squares. Because when we compute the new standard deviation for the distribution of the sample mean, that's what this reads, the standard deviation for the distribution of the sample mean, it's going to be sigma over square root of n. And what changes throughout this equation is the square root of n. Now, on the test, when we ask you what is the standard deviation for the distribution of the sample mean, so many people do not, when we say the standard deviation of the distribution of the sample mean, so many people just give us 3. They say, oh, it's 3. Well, that's what sigma is. Sigma will be divided by the square root of n. So all we do for this problem is take 3 and divide by the square root of 4 the first time, then 36 the next time, and then 64 the last time. So that's all I'm doing right here. If you watch the numbers I put in, I'm just solving for 3 divided by square root of 4, which is 1.5, 3 divided by square root of 36, which when you figure this out, it's 1/2, and then 3 divided by square root of 64, which is 3/8, which is 0.375, which is, yeah, just solve it out. Okay, so here we are, and we solve out 1.5. That's not 1.5. Next one was divided by 36. That's 0.5. You notice it's getting smaller as the n increases because you're dividing by n, and then 0.375 because 3/8. Oh, what? 2 decimals? You gotta be kidding me. You gotta be kidding me. Give me a break. So now this asks about, is it normal? Well, it becomes more normal as n increases. So which one would be the most likely to be normal would be the one with the largest sample size, which is the pallets. Regardless of the underlying distribution, the pallets are going to be the most normal because it approaches the normal as n increases. And that's the central limit theorem. As n increases, the distribution of the sample mean and sample proportion become more normal. You can see it right here with this one with a sample size of 2. That means you take 2 observations and average them and keep building this distribution. It's not going to look so perfectly normal. But as we increase n, you can see here samples of 5 and the average of a 5, and we show what it looks like. It looks more normal. It starts to get more normal and tighter for larger samples. Even if you have a skewed distribution, it'll still have some skew at the smaller sample sizes, but it becomes more normal and tighter by a factor of the square root of n. Notice that this standard deviation is 6.25. Well, if I divide 6.25 by the square root of 25, because we take the original standard deviation of 6.22 and divide by the square root of 25, which is divided by 5, 1.24, there it is, right there in the simulation. And the mean is the same value because the mean doesn't change. So that's really cool. I love that simulation page right there. It's really good stuff. Let's do the next question. Who's here watching, getting these questions done? We might be able to get them all done. Anyone here watching, getting them done, being like, I am getting this assignment done. Okay. A standardized test has a mean of 144 and a standard deviation of 9 and is unimodal, symmetric, normal. Mia, good job. And test preparation organization has a small class of 9 students, a large class of 25. Both publish the means. Well, we'd expect both classes to have the same mean. We'd expect the sampling distribution of the mean classes scores to be for each organization. They're both going to have the same mean. No. Oh, would you expect? Wait. No, it's unimodal and symmetric for both. The underlying data is unimodal and symmetric. So since the original data is unimodal and symmetric, a sample size of 9 and a sample size of 25 will lead to normal distributions. Both will be approximately normal. And I'll show you. The test for the large enough n, the first thing... Oh, I changed this slide. Let me change it back. The first thing you do on a test for a large enough n is you find out the shape of your data. They stated that the original data was normal, unimodal symmetric, which means a sample size of 1 is large enough. Then they said our sample sizes were something like 9 and 25, and both of those are large enough. This is how you do the large enough n, because you check the original shape, then you know the associated sample size, which is below it. And if you have a large enough sample size, the distribution will be normal. So yes, both of these sample sizes were large enough so that the distribution of the sample mean will be nearly normal. Great job, Alexis. If the organization has a graduation mean of 153, they'll take a full paper advertisement. A mean score of 153 is this many standard deviations from the mean for the smaller and this many standard deviations for the larger. It's more likely for the smaller. I'll explain why, and I'll find the answers. So the original standard deviation is 9, which means when we look at this, and I need to grab this data, the standard deviation of y bar for the smaller is going to be the original of 9 divided by the square root of 9, which that's going to be equal to 3 when you solve it out. That's because this is sigma over square root of n, and we need to make sure we use the sample size according to the smaller or larger one. Standard deviation for the larger class is going to be 9 divided by 5, which is going to be 1.8. And with this right here, we can find the difference. I think it was 154, was it? 153. 153 minus 144 is a difference of 9. And with a difference of 9, 9 divided by 3 is 3 standard deviations up for the small class. 9 divided by 1.8, because we're figuring out how many standard deviations it is away. That one I can't do so well in my head. No, is it 5? It's 5, isn't it? Yeah, it is 5. Okay. Just check the math. It's 5. Nice math. And so that's got it. It's more likely for the smaller class. 3 and 5. Should do it. Now we have 138. 138 is going to be 6 below. So we can use the same sort of math that we just had, but change it to 6. Because remember, we're looking at 138. And so that's 6 below. So we can just take the 6 and divide by. And it's probably 3.75. Let me find out. No, 3.3. That makes more sense. Okay. There you go. That's how far, and we're just figuring out first up top here how far it is away, and then we're dividing by. We're literally doing y bar minus the mu divided by the standard deviation of y bar equals z-score. And so this is where we're doing the difference divided by the standard deviation. That's what that is right there. And this is y bar minus mu, which is equal to the difference. I got in trouble for not labeling my work as a kid all the time. So 2 and 3.333. So once again, the smaller class would be more likely, or the smaller class would be more at risk because they have more variation in them. 3.33. There we go. Okay. Oh, they made this one so easy. It's all about the notation, though. You gotta know your notation. A waiter believes that their distribution of tips is slightly skewed to the right. That's telling you the shape with a mean of 9.6 and a standard deviation of 5.4. Explain why you cannot determine the probability that a given party will tip in at least 20 from one tip. It's because the original data is not normal. The distribution is skewed, so we can't use the normal techniques on it. So good stuff. Can you estimate the probability for the next 4 parties? Well, I don't think the central limit theorem is going to kick into play, because we don't have a large enough sample size. So it's like, well, it's skewed. What if you did it for 4, which I don't have? Well, it'd probably still be skewed. I would say no. Sampling of 4 is not large enough for the central limit theorem, which states that the distribution will become more normal and the mean will stay the same and standard deviation will get smaller. Probably not going to happen. What about 10? Maybe. Maybe. So I think right here. Yeah. And they calculated the new standard deviation with, really? With this one, they calculate the new standard deviation down here because we can take the original standard deviation of 5.4 and divide it by square root of 10. So we take 10 square root and we take 5.4 and divide, really, 5.4 divided by square root of 10. There we go. So that's the new standard deviation. The mean would stay the same. So they're showing you how the distribution changes right there. I guess we might end with the waiter waitress one. Or are the other ones easier? Are they really? Oh, let's do this one real quick. Someone will be like, you skipped it. We'll come back to waiter waitress. This is 5. Question 5. Okay. 49.23. Which of the following is not a condition to check to estimate the mean of a population? To estimate the mean? Oh, it's not a condition to check. Well, it says to estimate the, because it's not saying to calculate a sample mean. That's where people might be confused on this. It's saying when you try to figure out the true population and its characteristics and the sampling distribution, they really should get more specific on this. It's success failure, but I was looking at the way the question was worded. I almost don't like it. Success failure is categorical data. So we did this one during class. I might take a quick break. CEOs is skewed to the right. And then it's going to show. Oh, it doesn't normalize. Well, we have more time, as in, you know what, let's do the full thing. Let's do it. Oh, wait a minute. I got to restart this question. Yeah. Let's do waiter, waitress. Waiter, waitress. Waiter! You get that question, you're a 2000s kid. 43. Waiter. Okay. This is one of my favorite questions right here. I think we'll probably end on it. A little bit of break between classes. The number one thing you have to do for every question is mark the notation. You have to mark the notation. So it says the mean is this. So that's mu. The standard deviation is this. That is sigma. And it's stated as facts, not as sample data. The next thing it says, they weight on 60 tables. That is sample size that they weighted on. The distribution is skewed to the right. So we got a monster man going on right here with a little bit of a right skew. Now, it doesn't say heavily skewed to the right, so a sample size of 25 is what we would need according to the large enough n, so we should be good here with what we have. Estimate the probability they'll earn at least $650. To earn $650 off of 60 tables, you would take $650 and find out that you need an average tip of, I believe, around $10.83. Is that right? We'll find out by dividing the numbers, but let's find out right here by dividing the numbers. So that's 650 divided by 60. There it is. So this is the average tip needed. You'd have to average on 60 tables $10.83.33. So is that possible? Maybe. So we're going to draw the distribution right here of what your tips would look like. Mu y bar equals mu. The center of this distribution is going to be mu, which is 8.2. Now the spread is going to be the standard deviation of y bar, which is sigma over square root of n, which is going to be the original standard deviation of 6.10 divided by square root of 60. So that's going to be about 1.2 or so, something like that. 60 square root, and, oh, I'm off. 6.1. Yeah, that's right. Double checking my math. Yeah, I misthought. So you notice that's about 0.8, which means this goes up to about 9. I'm just writing it kind of nicely here. 10.6. Ooh, look at this. This is off the scale here. That's off the scale, which means very low probability. We're not probably going to get this. So if it says to 4 decimals, we might be able to guess it because it's probably around a very tiny probability to 4 decimals, maybe something like that. We got it. There we go. Now, how do you get it without doing that? You have to go to the apps. So we're going to go to the apps right here and actually get the real answer, because remember, we're using the normal curve. So we're going to go to the normal curve, and we're going to put in our mean of 8.2. We're going to put in the standard deviation of the value we found, and it draws the curve like I drew it out right there. And then we want to figure out above, so we have to go find the probability going above something, 10.8333. And then we change the decimals right here to 4 decimals. And did I get it on the dot? Wow. That's why you've done too many of these problems. The total amount they earn on the best 10% of weekends would be what? If I get this one, that'd be amazing. I can cheat and get it if I know some answers. It's about $1 more, about $9.20 times 60 is what? 9 times 6 is 54. 540. And then another, it's like 5, 1, 2, 3. Yeah, if I got that, I would have been like crazy. It's easier with the applet. Go to the applet. Let's go here to find x using p-value, and we want to go to the top 10%. And there's the top 10%. This is the average tip on the best 10% of weekends. Now remember, they weighted on 60 tables, so times by 60, and there it is, 552.55. Come on. Really? Really? We'll do that problem again more slowly. I kind of did it quickly because I want to take a quick break between classes, but I hope people are figuring out these problems, understanding them. When you know the tricks to them, they're a lot easier, especially like ones over here that look complicated, and then you realize it's just asking you what the mean is at all points, and the mean doesn't change. So this one right here, you can get half of it right for free because the mean doesn't change. And then the standard deviation gets smaller by a factor of square root of n. So you would just divide by a factor of square root of n to get the answers right for the other questions. And the theoretical values are going to be reasonably close to, because simulations show reality. So this is a left-skewed histogram, and the simulations are going to support this. The peak of the histogram is going to stay about the same. The shape of the distribution is going to become more normal, and the variability is going to decrease as we increase n right there. And it doesn't always work. There's no rule of 30. You need very large sample sizes when there's very large skew. Since distribution of the means, the rule of thumb does not hold for highly. That's it. Well, we did most everything. Till then, bye for now, everyone. Bye.